All right, so we're going to look at exponential and logarithmic models. So mathematical models are equations that you can use to model phenomenon in the real world to help you make decisions and predictions. And so there's many mathematical models out there, but the four most common, not just in general, but for exponential or logarithmic functions would be these four right here. So we've already talked about 1 and 2. This is just another version of the Pert formula. So like when you are trying to find the amount of money in your account, if it's compounded continuously, use what's called the Pert formula, which would be like the amount in your account A is equal to P times E, where E is just the base, which is around 2.7 times the rate times time. But it doesn't just need to be used for bank accounts. It could be used to model all types of things, and we'll look at those things. So it's the same formula, it's just instead of B, we have R, instead of A, we have P, and instead of Y, we have A. It's the same idea. And the only difference between a growth and decay, because for either one of these, the base is E. So that's greater than 1, which would make you think they're both growth. But if your rate is negative, that'll make it decay, because like E to the -1 power, if we factor that -1 out from like the B times X part, E to the -1 is just 1 over E, and E is around 2.7. So you can see that it does still follow that rule that if you have a base that's between 0 and 1, it's going to be decay. And the reason why we use E is because it's a base to model something that's compounding continuously. So if you have like a bank account where you get 2% interest every month, like on the last day of that month, you're not going to get that 2% interest, but on the first day of the next month, then that 2% interest is applied to your account, because that's just how the rules of the bank work for that particular account. But something like ice that's melting, like the temperature isn't going to decrease by 2% every minute or every hour. Like it's just going to continuously decrease. Or like if there's a growing population of bacteria in some sample, like the bacteria is not going to be like, all right, let's all multiply every month or every hour, every minute, every second. It's just going to continuously do that. All right. And for logistical growth, you watched the video last class about like the spread of the coronavirus. And that's a great example of a logistic growth. And what logistic growth is something that grows exponentially at first, but in the real world, like nothing could grow exponentially forever, because then eventually it's going to get so ridiculously high, it's not going to really model anything in the real world. So even something like a pandemic, like let's say there were no restrictions put into place, no one wore any masks, and everyone just wanted to get the virus, all right? Then eventually it would start to slow down on its own, because you can't get it more than once in a certain period of time. So once everyone has it, there can't be any like new people who get it. So there is like a limit, and that's the population. All right. And that's true for all types of populations that grow exponentially. All right. Eventually you run out of space or resources or whatever, and it's going to level out. So that's what logistic growth models are great for. Things that grow exponentially at first, but eventually run out of space or time or resources. And then logarithmic models, we probably won't get to that, but they're used for things like the Richter scale, like the way you measure earthquakes. And there's many things that grow according to like a logarithmic model. And I'm sure you'll study those a lot in calculus or other math classes. So just in the notes, feel free to reference it. It's just a couple things that we've already looked at for exponential growth and decay, all right? The horizontal asymptote, because I'll never reach 0. It's going to infinitely approach 0. It's going to be the x-axis unless you shift it up and down. All right, the domain is all real numbers, because you can raise e to any number and get a real number, whether it's positive or negative. But e to a certain power, as long as a is positive, is going to get, well, it doesn't actually matter. It's going to get closer and closer to 0 as the exponent becomes more negative, but it's never actually going to touch it. But as the exponent gets really large, then like 2.7 to larger and larger powers will just get larger and larger. So that's why the range goes from 0 to infinity. Because of the asymptote, there's no x-intercept. Y-intercept is where x is equal to 0. And it's increasing, meaning it's exponential growth if the rate, if k is greater, sorry, let me do that. It's positive, or if the rate is negative, like, you know, the population is decreasing by 5% every year, then you'll see it's decreasing, it's decaying. All right, it's going to approach a specific number. All right, so you may have done these in science before, and so they're called half-life problems. So this would fall under the exponential decay category. So the half-life of an isotope refers to how long it takes to decay to half its original value, or its weight or mass, or whatever the context is. So something like, let's even before we even go to this example, something like if you ever took an Advil or a Tylenol or something like that, maybe you have a headache, if you ever read the back of a bottle, it says, you know, don't take more than one dose every 4 to 6 hours. And that time, that 4 to 6 hours, is directly related to the half-life of that medicine that you're taking. So let's say you take Advil, right? The half-life of Advil is about 1.8 hours, because I've Googled this a lot. All right, it's about 2 hours, okay? So what does that mean? If you take, I don't know, how much is in a milligram? Let's say I don't know what a typical dose of Advil. So what is one dose of Advil? 200 milligrams, right? So you take 200 milligrams of Advil right now. It has a half-life of 2 hours. So that means in 2 hours, 100 milligrams would remain. So it went from 200 milligrams to 100 milligrams. Then in another 2 hours, so 4 hours from now, we get cut in half again. So now 50 milligrams remain. So you shouldn't have too much of this in your system. So that's why they say take it from 4 to 6 hours, because once you get below, let's say 50 milligrams, there's no longer enough in your body to do anything, because your body is breaking it down. And the time it takes to break it down is called the half-life. So if this had a longer half-life, then they would probably say, you know, the effects would last longer. It would last, you know, more than 4 to 6 hours. But if the half-life was shorter, that means the body's breaking it down faster. So it only takes less time for your body to you know, metabolize half of it. And eventually it's going to keep breaking it down half and a half and a half until there's like virtually nothing left in your system. So that's why like things wear off, because of the half-life of like how fast your body breaks it down. So caffeine is another example of half-life. So let's say you drink a cup of coffee in the morning, right? Usually feel those effects for a little bit, but they eventually wear off, right? Just because caffeine has a half-life of about 6 hours. So the caffeine goes in your body. Let's say you take 100 milligrams of caffeine, then in 6 hours, there'll be about 50 milligrams left, all right? So you gotta be careful when you drink that second cup, because you're not just drinking new caffeine, you still have the old caffeine that's in your body. So with medicine, you know, you have to know the half-lives, or else you may overdose, which is bad. So if you drink a cup of coffee at 7 a.m., how much caffeine will remain in your body at 3 p.m., all right? So we drink a cup of coffee. So I don't know how much caffeine is in a cup of coffee. So let's look that up. How much caffeine in coffee? All right, 95 milligrams. So I'm gonna get out my piece of paper and write that down. So 1 cup is 95 milligrams of caffeine. I gotta turn my camera on too for my. All right, so it has a half-life of 6 hours, so I'm gonna write that down too. Half-life 6 hours. And we drink a cup of coffee at 7 a.m. So I know you can't see my paper. I will project it in a second. But if we drink a cup of coffee at 7 a.m., we're gonna start counting at 7 a.m. So we'll say T = 0 is equivalent to 7 a.m. All right, and we know that the amount of caffeine in your body at that time would be 95 milligrams, assuming you just chug it real quick at 7 a.m., which isn't really feasible, but in math, you got to make assumptions. So we'll just assume that at 7 a.m. on the dot, there's 95 milligrams of caffeine in your body, where practically speaking, it's going to take, some time for you to drink that coffee. So how much caffeine will remain in your body at 3 p.m.? All right, so if T equals 0, so now I'll project my camera so you can see what I'm writing. I wrote down 8 p.m. I don't know why I did that. I meant to write 3 p.m. Actually, I do know why I did that. All right, well, okay, so if T equals 0 is 7 a.m., T equals 1 would be 8 a.m., 2, 9 a.m., 10 a.m., 11 a.m., 12 a.m., 1 p.m., 2 p.m., 3 p.m. So that's 8 hours away. So T equals 8 would be 3 p.m. How much caffeine will be in your body? So first, let's make a table so we can understand what half-life is. All right, so we'll start off at 7 a.m. So that's T equals 0. You have 95 milligrams of caffeine in your body. Now, the half-life is 6 hours, which means 6 hours from 7 a.m., which would be 1 p.m., you have half the amount of caffeine left in your body. So that would be 47.5 milligrams. So that's all it means. It takes that much time. That's one half-life for this to get cut in half. So what that means is that in another 6 hours, the amount of caffeine in your body doesn't reduce by another 47.5. All right, that would be like a linear growth or decay where you subtract the same amount every time. This is exponential decay. So it gets cut in half again, not subtracted by the same amount. So at T equals 12, you would have half of 47.5 milligrams of caffeine in your body, which comes out to be, as a decimal, 23.75 milligrams. Now, T equals 12 would be 12 hours from 7 a.m., so that's 7 p.m. So I always think for half-life, it's good to do like a quick, and you don't have to write it all out like this, but at least you could do something like this in your head so we can get an estimate for our answer, because it's always good to do that in any word problem first, kind of estimate if possible, so that you get a better understanding of what's going on. And also when you get your final answer, you could see if it fell close to your estimate. So what do I mean by that? Well, 3 p.m. is in between 1 p.m. and 7 p.m. And we know at 1 p.m. there'll be 47.5 milligrams. At 7 p.m. there'll be 23.75 milligrams. So 3 p.m. is somewhere in between those two times. So that's T equals 8. All right, so the amount of caffeine in your body should be somewhere in between these two values. So when we finally find our actual answer that's very accurate, we should hope that it's in between these two values, or else we did something wrong, either on the estimating side or the calculating side. All right, so that's all half-life means. And if you were to keep doing this, even the next day, there's still some trace amounts of caffeine left in your body. 6 hours later, you would have half of this amount. And then 24 hours later, so a full day later, you would have a quarter of that amount, which is probably around 6 milligrams. So if you drink a cup of coffee one morning at 7 a.m., the next day, 24 hours, there's still some trace amounts of caffeine in your body, according to this model. All right. So now let's actually find the actual number. Okay. So let's look at what's happening here. All right. At T equals 0, we had 95 milligrams. All right. And then at T equals 6, we cut that in half. Okay. And then at T equals 12, we took the amount in your body at 6 hours and we cut that in half again. So it'd be like multiplying this by another half, which is the same thing as squaring it. And then after 18 hours, you cut it in half again. So you can kind of see this model forming. Your base is 1/2. And every time the time increases by 6 hours, this exponent, and you can even put an exponent here as like a 0, like this exponent increases by 1. All right, so what we could do for our model is write it as y equals 95, where that's your initial amount, and y is the amount of caffeine in your body at any time, times 1/2. And since t is our independent variable and t is in hours, we can raise this to the t over 6 power, because every time the time increases by 6, we want our exponent to increase by 1. So, right, if we plug in 0, the exponent's 0. If we plug in 6, 6 over 6 is 1. If we plug in 12, that's 2 half-lives, our exponent is 2. 18, that's 3 half-lives, the exponent is 3, and so on. All right, so to generalize this, you can always use this as like your half-life model. Which I don't know how great you can see that, but let me zoom in a little bit. Where it's just A, where that's like your initial amount, and I'll put a little sub-0 there so you know that's when time is 0, times 1/2, if it's a half-life, to the t over whatever your half-life is, to ensure that every time t increases by 1 half-life, your exponent increases by 1. Yeah, Nick? Can I take a picture of that? Yeah, sure. And sure. You can always refer back to the video too. It's also in the notes, just so you know. All right, so now we can use this model to figure out how much caffeine is in the body after 8 hours. So we'll just pull up our calculator. Open up a new doc, new calculator. So we got 95 times 1/2 to the, since it was 8 hours at 3 p.m., to the 8 over 6 power. And because I didn't hit control equals, it gave me like an exact answer. So an approximate answer would be about 37.7 milligrams. Which checks out according to our model here. Oops. Because we estimated it between like 47.5 and 23.75. All right. So now, if I asked you this question here, exactly how it's worded, we're done. We did what we needed to do. But I did bring up something at the beginning of class, that the model for exponential decay is this right here. So I just want to go over how you can rewrite the model that we just did in this form, y equals a times e to the negative bx power. So how can you rewrite this with a base e? Because why would you want to know that? Well, someone else might use this as their model with base e instead of base 1/2, and you want to be able to compare them and go from one model to the other. And it's really not that many steps more. So let me show you what I mean. All right. If we take y equals a times e to the negative bx power, all right, a is still going to be 95 because that's still our initial amount. But now we just have to figure out what b would be so that this is the same exact graph as this. So what we could do is use properties of logs, all right? We could take y equals 95 times e and raise it to the natural log of 1/2 power, because this e to the natural log of 1/2 is equal to 1/2. Anytime like the base of your exponent is the same as the base of your log, it's just going to cancel out and equal whatever's inside the log. And that's just because that's a property, but you can see it by putting it into log form. All right, so e to the natural log of 1/2 power is equal to 1/2. base exponent answer, if we put this into log form, all right, the log base e of 1/2 is equal to the natural log of 1/2. All right, and that's true because natural log means log base e. All right. So if I were to just replace 1/2 with e times the natural log of 1/2, and then leave the t over 6 here. All right, now I can rewrite that as 95, or y equals 95 times e, and then I could just write this whole exponent as the natural log of 1/2 times t over 6, but I can now put the over 6 part under the 1/2, and this is just the value for b, like in this model here. So if we pull up our calculator, we can estimate that as a decimal. We can say the natural log of 1/2 divided by 6 as a decimal is that, which means y equals, or we'll go f of x, we'll define it as 95 times e to the, we'll go negative 0.11552, we'll round up. Let's go 2. All right, times x. And if I do g of x is equal to 95 times 1/2 to the x over 6 power. That's not what I wanted to do. I have to do colon equals. All right, you should know how to do this stuff on the calculator. And I'll erase this. All right, these are both the same exact models. All right, if I do, remember, if we plugged in 8 hours into this one, we got 37.7. If we plug 8 hours into this one, oh my gosh, I gotta hit control equals. I would get the same value. Now they're slightly different only because I had to round this number, which is why I sort of like this better, because it's just simpler and more exact. This you have to round, but you will see models of half-life like this. And I just want you to see like how they come up with that, right, where that comes from. And if we were to graph both of these, they're the same exact graph. They're just, you're rewriting them different ways. Okay? And then, so that's all kind of summarized here, like in the notes. I know it's not really big, but everything is here for you for future reference. There you go. And then this tells you how to do it directly when the base is E. And this shows you how to do it directly when the base is 1/2. And then what we just did was find it when the base was 1/2 and then put it into this form. All right, so there's a lot of different ways to do it. All right, now let's talk about Otzi. All right, who is Otzi? Well, he's got to be famous because he has a Wikipedia page. All right, that's where I found this information. So he's also known as the Iceman. All right, many people in history have had the nickname Iceman. He is one of them. He is a well-preserved natural mummy of a man who lived between 3400 and 3100 before Christ existed. All right, so to put this into layman's terms, this was a man. No, we don't know too much about him, but we do know how old he is. We do know when he existed. All right, and he was found in the Alps. So I don't know exactly what happened, but possibly he was in the Alps skiing or something, walking around, and then, I don't know, tragically died. I'm assuming it wasn't a natural death, or maybe he was, but he got preserved, and maybe he got frozen. He got hit by an avalanche or something. And then recently, like in the last 100, 200 years, I don't know exactly when, they found him and they were able to estimate his age. So he's very famous because it's not often that you find a well-preserved human mummy from these time periods. It's very rare. So they did a lot of scientific studies on him. So first, before we think about how they figured out how old he was, Can anyone name a famous descendant of OC? Because he existed a long time ago. So we had to have like, so a long time ago, if you have 2 kids and then they have 2 kids and then they have 2 kids and then they have 2 kids, like you have a lot of descendants at this point. What did you say?
Kind of looks like Ryan Fitzpatrick.
Wow, you're right. He does kind of look like Ryan Fitzpatrick. Does he resemble me at all? Because that is my great grandfather or uncle or cousin. I'm not sure, but I am related to him. I do know that. And how do I know that? Because my uncle, so he's my grandma, she had 5 kids. One of them is my mom, and her brother is my uncle. So I'm a descendant. We come from the same tree. My uncle did a 23andMe like a year or 2 or 3 ago. And when you do those, it tells you like where your origins are from, and it tells you if you're related to any like famous people in history. And he was one of them. So so everyone treat him with respect. This is my great grandfather, great looking guy, great body, great sense of fashion, an excellent hunter, great beard and long hair. So we have that in common, the hair, not really the beard. But yeah, so kind of a big deal. So you can get autographs later. But anyway, what I'm really interested in is how did they figure out how old this guy was? Like they just find a well-preserved mummy, and they find like fossils all the time. And they're always like, oh, this is from like the Jurassic period. Like, how do you know that? Like someone could have just put that there. But there is a way where you can date an artifact, right? And you may have learned about this in science, and your science teacher could probably explain this way better than I can, but I'm going to try to explain it to you because it is connected to math. All right, what they did was they used radiocarbon dating. All right, so that's a type of exponential decay which calculates when an animal or plant died within 1% error. So this method was discovered in 1949 by Willard Libby. All right, so we got to give him props. And also my favorite hot dog place is called Libby's, so I had to put that in there, but sadly closed due to COVID this summer. I'm still not over it, but anyway, I digress. It compares the ratio of 2 isotopes of carbon in an inorganic artifact or fossil to the ratio of those 2 isotopes in the air. Carbon-14 is radioactive, and it has a half-life of 5,730 years. It occurs in small quantities in the carbon dioxide in the air we breathe. Most of the carbon on Earth is carbon-12 with other science stuff. All right, so I just read that straight off the slide. But let me try to explain how this works. And there's another slide here. But when something is breathing, like a plant or an animal, all right, we're breathing right now. All right, we take in stuff from the air. So we're constantly replacing the carbon in our body. So when you're alive, the carbon in your body is the same as the carbon in the air, in the atmosphere. But when a plant or animal dies, it's no longer breathing, so it's no longer taking in the carbon that's in the air. So the carbon that was last in your body starts decaying because it's not getting replaced. And scientists can look at tree rings because tree rings are like a very straightforward way of calculating time because every year the tree grows like more bark and it creates rings when you cut it. So they can like cut an old tree and find the carbon inside a tree ring and count the rings and see what the carbon was like in the air during specific time periods, because it does change over time. So they could compare that to the carbon that decayed in the body or the plant or whatever to calculate how old it is, because we know the half-life of carbon-14, all right? And you could calculate that by just taking 2 of these isotopes over time and then writing a model, all right? So let me finish reading. They determined the ratio of carbon-14 to carbon-12 in the air for the last 60,000 years using tree rings and other samples of known dates, although the ratio has changed slightly over the centuries. So as long as a plant or animal is alive, the ratio of these isotopes is close to the ratio of that in the atmosphere. When it dies, it decays and it's not replaced. So you can use the half-life by comparing carbon-14 to carbon-12 in the decaying sample and knowing the ratio in the atmosphere and the date the plant or animal died, okay? So let's do an example. So let's say you're roaming through the forest, you're going in for a little bike ride or walk, and you find an old piece of burnt wood, so like charcoal, and you take it into your lab, because we all have a lab at our house, and you put it under your microscope, and you notice that it only has 30% of the radioactive carbon-14 as a piece of modern charcoal. So you burn another piece of charcoal and you compare it. So you know the half-life of carbon-14 is 5,730 years. How long ago was the tree burned down? All right. So make a new doc, fresh doc. All right, so the half-life is 5,730 years. So if if it had 100% of that carbon-14 in it, then that means it just burned. It'd be like around 0 years old since it was burned. But then if it got cut in half, so it decayed to 50% of that ratio, then it's 5,730 years old. Then if it got cut in half again, so decayed to 25% of the amount, because a half of a half is a quarter, and that's 25%. You would add another half-life. So this would be the number for 50%, and this would be the number for 25%. So since we're looking for 30%, it should be somewhere in between these two numbers. So now if we take our model, we'll go y equals a times 1/2 to the x over 5,730 power, right? Well, we don't know the initial amount, but we know that now it has 30% of the initial amount. So now we have to solve for x. The only issue here is that we have two variables. But luckily, we can assume that this initial amount, like the weight of the mass, the milligrams of this piece of charcoal, you can assume it was like a positive number, like it had some weight to it. So we can just divide both sides by that. And then we get this. So like if this was representing like 100% of the original amount, that's 30% of the original amount. And now we just have to solve for x. And for a word problem, I'm fine with you just using the solve function. The only time I'm going to need you to solve this without like the solve function is when I specifically say, hey, solve this equation and show all your steps, which you should be able to do. All right. But for a word problem, just use the calculator. All right. And the way you would solve this is rewrite that in log form. So like your base is 1/2. So it'd be the log base 1/2. Your answer is 0.3. And your exponent is x over 5,730. And then you would multiply both sides by 5,730. All right, and we get the same exact number. All right, so that's how you do it without a calculator solve function. But there's our answer. We know that this piece of charcoal is around 10,000 years old. Okay? All right, do we got time for one or two more? All right, so Newton's law of cooling, okay? So first, write this down because I'm gonna like bounce around to some slides and I'll explain what everything means. But just write down that original model and then I'll explain how it works. And the quick way of explaining how it works is it's just exponential decay with the horizontal asymptote. So what does that mean? All right, so right now I just wrote down T of t is equal to A times e to the kt power plus T sub s. So before I even explain what these letters mean, let's just try to talk about what Newton's law of cooling is. All right, let's say I brought in a hot soup right before the beginning of this period. I came in with a nice big bowl of hot soup. All right, and I don't know the temperature of the soup, but let's say it was 100 degrees. And I just place it on the desk. And in this room, let's say it's 70 degrees. So Newton's law of cooling says that any object, the temperature of that object is going to approach the temperature of the surroundings. So whether it be the room or the outdoors or like an oven or a refrigerator or a freezer, exponentially. It's going to exponentially decay to the temperature of the room. So I want to draw this. Right, so this is temperature, that's big T. All right, this is time, that's little t. Okay. Here's my soup. My soup at time 0 is 100 degrees. It's too hot for me to eat. I like my soup hot. That's why I'm not going to eat it right away. I'm going to let it cool. All right. But yes, it would be very hot. But, well, yeah, let's think of like, but then again, I've been in it. I don't think so. At 100 degrees Fahrenheit, it wouldn't be boiling. Because like, ever been in like a hot tub with like the temperature? Like you go in there, it's 100 degrees and like it's uncomfortable, but you could sustain it. So 100 degrees might be a good temperature, but let's say I want it less. All right, but let's say that the temperature of the room is 70 degrees. Over time, that soup, the temperature is going to exponentially decay and eventually approach the temperature of the room. That's what Newton's law of cooling says. All right, so it's not going to decay according to like linear growth or decay. That would be pretty weird. All right, imagine that the soup was 100 degrees, the room was 70 degrees. So after the first hour, the soup like dropped 10 degrees and then it just kept dropping 10 degrees. So wouldn't be freaked out if I brought like a hot bowl of soup, left it in the room, then we came back tomorrow and it was like ice cold? That'd be weird. It'd be like, there's something going on here. All right. Now it could also work the other way. So let's say I took an iced coffee and that iced coffee was like a little, like almost freezing because it had ice in it. So it was like 32 degrees and I just left it in the room. Eventually it would approach the temperature of the room. It wouldn't go past the temperature of the room, it would approach it and it would eventually get warmer, but it wouldn't become hot boiling coffee. It would just like, eventually the coffee in the room would become the same temperature, all right? So that's all Newton's law of cooling says. It says that something will just approach the temperature of its surroundings over time without any other things being applied. All right, so now we wrote that down. All right, so what do each of these things mean? All right, first, uppercase T is the temperature. Lowercase t is the time. All right, T sub S is going to be the temperature of the surrounding area. So that's like the temperature of the room or the refrigerator or the oven, or if you leave something outside, right? Which obviously if it's outside, it could change. That would complicate things. So that's why in math, we assume certain things are constant. And then A is the difference between the initial temperature of the object and the surroundings, okay? Now you don't actually need to know that in order to complete this model. It'll just happen naturally, and I'll explain what I mean. But all you need to complete this model is 2 different temperature readings. If you know the temperature at 2 separate times, you could plug those in and then solve for K and A, all right? So A and K, they're constants that we're gonna solve for. And you also need to know the temperature of the surrounding area. All right, so now let's talk about a touchy subject. We might get emotional, especially for the sophomores. The freshmen, this might not mean anything to you guys, but all right, I want to talk about chocolate chip cafeteria muffins. All right, so let's have a moment of silence for them. Okay, they're gone but not forgotten, and they will be back. Now, a quick tangent about muffins. All right, I have an idea. So right now they're not selling muffins because of the coronavirus. You know, you don't want to eat and spread the virus. I get that, but essentially, they banned muffins for temporarily, okay? Now, in history, have you guys learned, now first, why are muffins so important? Okay, it was customary for kids to just leave class, say, hey, I'm going to the bathroom, and then come back with like a warm, juicy chocolate chip muffin. And I'm okay with that because they're so delicious, all right? But anyway, they're really good. Cafeterias sold these delicious muffins. You could go grab one at any time, and it's said that they're not around anymore. I think if they said muffins were back, I think 100% of the student body would come back to school. I don't think no one would be virtual. I think everyone would be back. All right, now, have you guys learned about prohibition in history class? All right, good. So you know what I'm talking about. Yeah, you're on the same track as me. So during Prohibition, and like, I forget when it was, like the 1910s and 1920s, they banned alcohol. And it was a good intention. They're like, alcohol, bad. People drink alcohol, they do bad things, let's make it illegal. All right, okay, makes sense on the surface. But then what happened? They banned alcohol, and people were like, well, just because it's illegal doesn't mean everyone's gonna stop drinking alcohol. So we created a black market. So that means that like illegal gangs, mafias, organized crime, they would sell alcohol behind closed doors, and they became very rich and powerful, and they took over the country. And it was a way bigger issue than people being drunk and drinking alcohol. Although that's another issue, but they created a worse issue. All right. So here's what I'm saying, and if you're on board, just give me a nod. We don't want, it's just in case the feds are listening, but I believe the school created a black market by banning the muffins. And I think we, as period 8 algebra 2, we could create our own mafia and gang, and we could sell these muffins on the black market, like on the DL, and then we could become rich and powerful, and then we just take over the school. And it's now no longer Ridgewood Public Schools, it's just our school. So if you want to join my gang, we could do it behind his back. And when someone gets caught, we could just like throw someone to him, like as a, like be like, hey, we need a fall guy to take the blame. Like we'll be behind closed doors, like working all the strings and collecting all the money, but what we could do is maybe we could get some 8th graders to like take the fall for us. And yeah, like we could recruit them, like they're impressionable, they'll do anything. And we tell them there's extra credit. We'll be like, hey, extra credit. And those kids will do anything for extra credit. And then we use them as pawns for our scheme. All right, so something to think about if you want to take over the school, that's my plan. Back to math, all right? So how does this relate to exponential growth and decay? The mafia part doesn't at all, but the cooling part does, all right? So a muffin was taken out of the cafeteria oven with an internal temperature of 165 degrees, all right? So what does that mean? I want you to write this down. I want you to write down 0,165. So that represents a point on our graph, all right? If we are modeling the temperature, we'll write this down later, but if we're modeling the temperature of the muffin over time, our first data point is when the time is 0, the temperature of the muffin was 165 degrees. All right, then we have another data point later on, but then the next part says it's placed into a refrigerator that has a temperature of 35 degrees. So I want you to write T sub S is equal to 35. All right, so that's going to be our horizontal asymptote. The muffin is going to approach the temperature of the refrigerator. So if we left the muffin in the refrigerator indefinitely, it would eventually be 35 degrees if the refrigerator stayed. All right, after 10 minutes, the internal temperature of the muffin was 150 degrees. All right, so we need that data point too to find our rate of decay. So we're going to write down 10, 150. All right, how long will it take for the muffin to cool to 70 degrees? So we're looking for the point question mark, 70. All right, so now I'm going to show my document camera and we can finish this problem. I'm going to zoom out just a little bit. All right, so here's our model. T is temperature, and we're going to make that in degrees Fahrenheit. And little t is time. All right, so we're going to put that in minutes because the data point they gave us was in minutes. So instead of converting that to 1/6 of an hour, we'll just keep everything in minutes. All right, temperature surroundings. So first thing we're going to do is plug that into our model. So we get T of T is equal to A times e to the kt power plus 35. Now we have to solve for A and K. So A was the difference in the muffin's temperature and the surrounding temperature. So it's going to be 130, but you don't need to know that. Why do I say that? Because if you plug in your initial value, which you'll always be given, right? So T of time 0 is equal to 165. You could just solve for A. So we get 165 for the temperature, and we plug in 0 for the time. And then this part becomes 1 because it's e to the 0 power, and anything to the 0 power is 1. And a times 1 is just a plus 35. All right, and then you solve for a by subtracting 35 on one side, and you get 130. All right, so now in our model, we have T of t is equal to 130 times e to the k times t power plus 35. Now we have to solve for t. Check that. We have to solve for k. And to do that, all you need is another data point. So what we're going to do is plug in 150 for the temperature and plug in 10 for the time and solve for k. All right, you could do this as long as you've understand everything we've been doing up to this point, like solving a exponential equation. You could solve for k without a calculator, but we're just going to use the calculator because it's a word problem and that's okay. All right, so solve 150 equals 130 times e to the k times 10 power plus 35, not equals 35, plus 35, and we're solving for k. All right, and you get k is that, which you could leave it exact if you want, or we could put that as a decimal. But just to talk through for 10 seconds how you would do that without a calculator. All right, if you subtract 35, you would get 115, and then divide 130 by 115, and that reduces to 23 over 26. Then you put it into log form, and you get the natural log of 23 over 26 equals k times 10, divided by 10, and you get that. All right, so now we'll just put that as a decimal. Okay, didn't want to do that. Oh. All right, and now we could take our model. So what I'm going to do is just copy and paste all this and make it a function. So f of x, we're going to define it as, all right, this, where I'm going to plug in x for the time and that value for k. So 0.01226. I did, because that's what k came out to be. And it makes sense because it's exponential decay, it's getting cooler. If it was getting warmer, it'd be positive. All right, and now it says, when will the temperature be 70 degrees? Since f of x equals the temperature, we can just do solve, when will f of x equal 70, and solve for x. And we see that it takes 107 minutes. All right, so the last thing I want to show you with this is just a graph. So if I graph that function, and if you just open up a new page and make this f of x, and then make our viewing window, we're going to make x min 0 to 180, because that's 3 hours. Well, let's go more than 3 hours. We'll go like 5 hours. And then the y min will go from 0 to 200, because that encompasses the range of the muffin. And then I'll also graph 35. You can see how this model shows the muffin's temperature over time, and it's exponentially decaying towards the temperature of the surroundings. And once you have your graph, you could trace it and see the temperature at all different times. Like, you start off at 165 degrees, then 30 minutes later, it's at 125. Now it's at 97.3. All right, and you can use this to model temperature over time if you just have the surrounding temperature, the initial temperature of the object, and then one temperature reading over time. And then the last thing is, if I reflect this is what it would look like if something cold was in a warm room. All right, so if you put something cold in a warmer room, or if you put like ice in the oven, it would get exponentially closer to the temperature of the oven, and it would look like that. So it's still exponential decay, but it's negative decay. All right, so I think that's all the time I have. So have a great day. Let me know if you have questions, and see you later.